In this video, we're going to talk about conditional independence. What is conditional independence? Well, recall that independence of two events A and B means that the probability of A intersection B is equal to the product of the two probabilities. Or alternatively, that the probability of A conditional on B is equal to the probability of A, and likewise for B conditional on A. So conditional independence says, suppose I have a third event C. So this is a new event. Conditional independence says that the probability of A intersection B given C is equal to the probability of A given C times the probability of B given C. Well, now you might think that this is pretty similar to the above, and it is, but they are distinct concepts because we can have cases with conditionally independent events that aren't independent, and we can have cases with independent events that are not conditionally independent. So let's look at some examples of those. Suppose I flip two coins. I flip the first one and I flip the second one. And let A be the event first is heads. Is heads. And B be the event that the second is heads. Now let C be the event that they're either tails tails or heads heads. Okay, so I think we can agree that the probability of A intersection B is equal to the probability of A times the probability of B. These are just two coins flipped independently. But what about P of A intersection B given C? Well, remember that the definition of conditional probability is P of this intersection with this. So this whole thing is one event, right? So we treat that as one event, A intersection B. Now intersection with this over here, intersection C, divided by the probability of C. However, looking at this, what events are in here? Well, this event A contains either heads tails or heads heads. So this is heads tails or heads heads. This is A. B is tails heads or heads heads, and we wrote out what C is already over here. So the intersection of everything is just the heads heads. But, so what do we have? This is now equal to the probability of just the set heads heads divided by the probability of C, which contains two events, which is a half. So we get a quarter divided by a half, which is equal to a half. However, over here, what do we have? We have, this is a half, because the probability that the first coin is heads is a half, and this is a half. And so this is 1/4. So what have we shown? Well, what about the probability of each of these guys given C. So the probability of A given C is equal to, now the only intersection of that is still heads, 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 divided by a half, and that's still a quarter divided by a half, so that's a half. And the probability of B given C is also a half. B given C. So the product of these two is a quarter. So if I'm given C, if I'm told that the coins either came up tails, tails, or heads, heads, then the probability that they're both heads is a half. But if I multiply the two probabilities together, then I would get a quarter. So, given C, the events A and B are not independent. Pictorially, we could draw out our sample space, get tails, tails, say heads, heads is over here, tails, heads, heads, tails, and C is this set over here. A is this set over here, so this is A, C, and B is this set over here, so this is B. Now, if I tell you I know I'm in C, well, then the only place that both A and B happen is here. So that you can see that the probability is a half, given that I'm in C, because this has half of the area, and this has half of the area. So we have two events that are independent, but if I condition on something, they're not independent. Now, what about events that are dependent, but they are conditionally independent? Suppose now I have 3 coins, and my sample space, omega, and we're going to write it as omega 1 union omega 2, and we'll see why in a minute. Let omega 1 be the set where all of the first coin is heads. So heads, use a different color. Let's see. Change that. Whoops. Okay. Heads. And then tails, tails. Heads. Let's see. Tails, heads. Heads, heads, tails, and heads, heads, heads. Now omega 2 is the same as above, except all of the first coin flips are tails. So same except first is tails. So now I tell you that the probability of heads for each of the subsequent 2 coin flips, given, so the probability, given that the first coin came up heads, so given that the first coin came up heads, using a different color to denote that, is 75%, so 0.75. And the probability that I get heads on each of the two next coin flips, given that I got tails on the first coin flip, is 25%. So we can think of this as flip a fair coin, fair coin, and then, depending on what I get, so if I get a heads, I take out a biased coin, and P heads, so then we have a new coin, where the probability of heads is 75%. So I have two drawers. I have drawer 1 and I have drawer 2. And I take the corresponding coin out of each of them. So if I know whether heads or tails came up, then the next two coin flips are independent of each other because I'm just flipping the same coin twice. But now, suppose I don't see the first one, and I say, well, what is the probability of getting heads on the second two coins? So this is equivalent to a probability of the set of the following. We have, so this is equivalent to the following probability. That the first coin is heads, and then we get two heads. And then that the first coin is tails, and then we get two heads. So what is the probability of each of these events? Well, in each case, we start with a half, so we get a half times 3/4 squared in the first case, and we get plus a half times 1/4 squared in the second case. So what's on our denominator? It's over 32, and we have 9 here, we have 1 here, so we have 10 over 32. Now, the probability of heads on the first flip is equal to, so now the probability of getting heads on the first flip, which we maybe will write as head blank, and that's equal to the probability of the set heads, and then heads, 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 tails, tails, heads, heads, and tails, tails, heads, tails. All right, so this is the set that we're looking at in the case of the first coin. So what's the probability here? So here we have a half, and then 3/4 squared. Now we have a half, and then we have 3/4 times 1/4, so 3/4 times 1/4. Now we have a half and 1/4 squared, and then we have plus a half, 3/4, 1/4. So let's add these up. We get, here we have 9 over 32 plus 3 over 32 plus 1 over 32 plus 3 over 32, and that gives us 16 over 32, or a half. So if I don't know what the first flip was, then whatever coin I grab, I flip it, and I say, yeah, I don't know which coin I got, so there's a 50% chance that it came up heads. Well, the same could be said for the second flip. So now I could say the same could be said for the probability of blank heads, because if I don't observe the first flip of that coin that I grab, then it has an equally likely chance of coming up heads or tails. We could write the same thing as we wrote up here, except just we have heads, heads, then we'd have tails, heads, 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 and tails, heads. And you'll see that you get the same probability out here. So that's also equal to a half. But the probability of blank heads times the probability of heads blank, that's equal to a quarter. A quarter, not a half. A quarter. And a quarter is less than 10 over 32. Why? Because if you observe the first flip and you notice that it's heads, a first flip of the coin that you grab from the drawer after flipping the deciding coin, then that gives you information. So the probability that you flip a second head, given that you flipped the first head after choosing the coin randomly, affects your belief about whether or not you'll get a head again, because it affects your belief about which coin you got. So this is conditional independence and conditional dependence.